Here we have a graph of weight versus height for 10 elderly men. What does this graph mean? Let's take this point here. This point represents one of these 10 elderly men. His height is 165 centimeters and his weight is about 57 kilograms. Now we're interested in the relationship between weight and height for these 10 elderly men. In particular, is there a trend? For example, if we increase height, does an increase in height lead to an increase in weight? We're also going to consider a linear dependence between weight and height. So how close do these points approximate to a line, a straight line? Well, it's not such a great linear dependence here. But we can imagine a line of best fit which is fitted to this data set. And we can consider how close these points are to such a line. So that's the idea of the correlation coefficient. The correlation coefficient, denoted by the letter R, is a measure of the strength of the linear dependence of two variables. In other words, how close are the points in our scatter plot to a straight line. R lies between -1 and +1. If R equals +1, then there is a perfect positive correlation between the two variables. If R equals -1, then there is a perfect negative correlation between the two variables. If R equals 0, then there is no correlation between the two variables. Here are some data sets with correlation coefficients written above each data set. Now, this first data set shows a relationship between two variables. The axes representing the two variables isn't drawn in, but we could draw it in like this. So it's y against x. We can see that all the points in this data set lie along a straight line. And that straight line has a positive slope. As x increases, y increases. So we say that the correlation is equal to +1. So R is a number that lies between -1 and +1. Now it doesn't matter about the actual slope of this line. We could imagine another data set like this here. Quite a different slope. But if all the points lie on a straight line, lie perfectly on a straight line, then R equals 1. It doesn't matter how the line is actually slopes. At the other extreme, we have perfect negative correlation. That's when R equals -1. Here, all the points in the data set lie perfectly on a straight line, but a straight line with a negative slope. So you can see that if we pick any point on this in this data set, increase x by say 1 unit, then y will actually decrease by a certain amount. So as x increases, y decreases. So the slope of this line is negative. The slope of the line actually would be the decrease in y. If we increase x by 1, how much does y change by? That's the slope. And that change is negative. Delta y is the change in y. If R equals 0, there is no correlation between the two variables. So that's this data set here. So increasing x by a certain value doesn't actually affect y. There's no linear dependence whatsoever between y and x. And there's no sense in which we could fit a straight line to this data. So R equals 0. And we have various values of R in between those two extremes in between the two extremes of +1 and -1. For example, an R value of 0.8, if R equals 0.8, then we have a strong positive correlation between the two variables, say y and x, because 0.8 is close to 1, and you can see here that all the points don't lie exactly on a straight line with positive slope, but there's a strong linear dependence. Here we have a weak positive correlation. We can see a certain trend in this data. If we increase x, we can see that y tends to increase. So as we move from left to right along the x-axis, the y values tend to increase. So we could kind of fit a line with a positive slope to this data set. And at the other end then we have weak negative correlation and strong negative correlation. So to get back to this data set, we have a positive correlation, plus 0.63, but it's not a strong positive correlation. It's not that strong anyway. So in general, we see that as the height of an elderly man in this data set increases, his weight increases. So that's given by the slope of this line. If we increase the height by 1 centimeter, then this change here is positive. But it's not a very strong correlation. It's not a very strong correlation between weight and height.